Go. Uh, Howdy, everyone. This is group number two, and today we'll be presenting the paper called Cascade, which is CPU fuzzing via intricate program generation. I'm Ishan Mandal,
And I'm Rebecca.
and we'll be presenting the paper. So let's get started. Okay. Before we go ahead and talk about the CPU, the actual Cascade fuzzer, we have to first understand what led the authors, what challenges they identified in like previous fuzzers and what led them to come up with this new paper. So the authors like point out two issues with previously existing fuzzers. First is completion. So the previously existing like fuzzers, a lot of them have programs which don't completely execute. So they execute maybe let's say 60 or 70% and they terminate. And rest of the 40% is totally unexecuted. And the second issue which they mentioned is called prevalence. So in a fuzzing instruction, you could have a lot of instruction which does the initial setup, and then you have the instructions which actually does the randomized like fuzzing. So the authors mentioned that like in the other fuzzers, there is an issue that a, a high percentage of instructions are actually just setup instructions and not actual fuzzing instruction. Now, traditional bug detection. So when you have something like in the previous models, we have something called a golden reference model. So what the other fuzzers do is that they go and like compare the value of registers with the golden reference model after every instruction. Now, this is problematic because it is like it has a lot of overhead because you have to compare after every instruction. And second is when you have an out of order machine, you might have like multiple copies, like multiple registers for the same multiple copies of the same register value. So the comparison uh, doesn't remain like straightforward. So here comes Cascade, which creates program which has an entangled control and data flow. It detects bugs by detecting non-termination. We'll discuss about that later in the slides. It generates long and complex programs, which has a higher likelihood of like undiscovering bugs. And when you actually find a set of instructions which trigger the bug, Cascade has something called automatic program reduction, which reduces the size of the code. Next slide. Okay, so why should you care about this paper? I have like four reasons to convince you why you should. So first is critical security risk in modern CPUs. So a lot of hardware vulnerabilities have been discovered in like recent years, and once you tape out the chip, it's very difficult to fix them. So you want to fix the bugs as soon as possible. And RISC-V is becoming a very ubiquitous in modern computing. So we want to have a rigorous, set of tools or a fuzzing tool which could identify bugs in RISC-V. And leap in testing methodology. Uh, Cascade introduces a new way to find bugs, which has like very less memory overhead compared to previous approaches. And the best part about Cascade is that it's open source. So your code base, you can see the code base. The authors have uploaded the code for like the public can view it. And if you're like brave enough, you can also go ahead and maybe become a contributor in the code itself. Next slide.
So, for the background of Cascade, I'll start by describing the difference between hardware and software fuzzing. So, software fuzzers don't require a structured input. Random mutations work as well. And to detect bugs, software fuzzers commonly rely on two techniques. They either look for crashes. Crashes, of course, as we all know, is the unexpected termination of a program, or they use sanitizers, which are checkers that are embedded in code to catch issues like buffer overflows. So as you can see in this diagram, the top half of it is software fuzzing. Generic data is fed to the software under test. The goal is to explore as many execution paths as possible and to find unexpected behavior. If the program crashes, it indicates the presence of a bug, which is captured in the yellow box on the right. Now, unlike software fuzzing, we can't just feed random data into a CPU. This is because a CPU is bound by rules, either of the ISA or the rules of a bus protocol. So, what hardware fuzzers do is that they generate structured input programs that follow ISA guidelines and bus protocols. These programs run on the CPU under test, and to detect a bug, the commonly used method for hardware fuzzing is differential fuzzing, in which the same instructions are given to both an instruction set simulator, which serves as a golden reference model, and a CPU under test. And the output is compared. If there is a difference between the two models, we know that there's a bug. However, this method has its own challenges. This is because comparing every instruction in real time is expensive and complex for CPUs. Mapping hardware states to software visible registers isn't always as straightforward. Now I'll explain two problems with traditional hardware fuzzers, namely completion and prevalence, that Cascade aims to solve. So as you can see in the example that I have given on the screen, uh, this is an example of a code generated by a traditional hardware fuzzer. So we have three load instructions which are involved in setup and one fuzzing instruction which is randomized. And then after that, due to an invalid address, the program terminates. Now in this example, there are a total of 7 instructions, out of which only the first 4 are actually executed. So the completion rate is only 4 out of 7, which is around 57%. And only one is prevalent. That means only one out of the 4 instructions that were actually executed was involved in fuzzing, giving us a prevalence of 25%, which is very low. Now, Cascade solves this by achieving both high completion and high prevalence. Now, in this example, this is something like what a code generated by Cascade would look like. There is only one instruction that is being involved in overhead, and the rest, all of them are being used for fuzzing. This gives us a completion rate of 100% since all the instructions are actually executed. And since there is only one instruction that is involved in setup and the rest are fuzzing, this gives us a prevalence of 7 out of 8 or around 87%, which was 25% for the previous example. Another challenge faced by fuzzers is how to generate valid programs with a high degree of dependency between data and control flows. Now, why do we need a high degree of dependence? This is because the more dependent that a program is, the more likely it is to explore more complicated and interesting execution paths, and the more likely it is to actually find a bug. Now, in the example on the left, we see that the first two move instructions are independent of each other, and the compare instruction does depend on the previous two move instructions, but it is not as dependent on each other as the example on the right, in which every instruction is dependent on the result of preceding instructions. Now, if there is such a high degree of dependence, as seen by the programs generated by Cascade, it is much more likely that a bug would be found.
Okay, so now let's talk about the all the building blocks of the Cascade fuzzer. So as you can see on your screen, we have the Cascade fuzzer itself is made up of like it executes in like 4 stages. So your first stage is intermediate program construction. Second is your ultimate program construction. The third is when you actually run the program under DUT. And then you identify the buggy test cases, and you do something called an automatic program reduction. Next slide, please. Okay, so our fuzzer starts with creating a basic block, a group of basic blocks which are like stored at like different memory locations, and all of them are like connected using a jump instruction. So before we like build a full-fledged basic block, we do something called a asymmetric ISA pre-simulation. So it's a novel method for generating instruction without having significant overhead. So what we do is like we start by creating a program which has a fixed control flow and randomized data flow. So what I mean by that is like the decision of the branches in this intermediate program is like fixed. So there is no decision like whether to take or not take the branch. So the decision is fixed, and using that, we first create a lengthy program, and then we insert all the dependencies. And the best part about this is the instruction set simulator is used once per program, not at every uh, step. So next slide, please. So here we have an example. So let's say this is a basic block, and what we do is we have some load instructions. X5 and X6, we load two immediate values. And if you can see in the branch instruction, we have something called which you would see like branch equals to X7 comma X7, which is always going to be true. So you have a branch taken every time in the intermediate program, and there is no control, like we have a fixed control flow in this program. Also, one thing I forgot to mention is that uh, Cascade also has a list of like known bugs. So bugs which we were previously discovered, they are like not if those bugs are triggered again in the fuzzing step, we have a list of previously known bugs and we don't rediscover them and waste our time in that. Next slide, please. So in the previous slide, we had an intermediate, like we had an intermediate program which had a fixed control flow. Now what we do is like transform those intermediate programs into fully randomized test cases. Now, as you can see, that branch equals to has been like it isn't like a trivial x7 comma x7. It depends on like two register x9 and x5, which are being modified in the like which depend on the XOR and the add immediate instruction. And you can see like the written instruction which had like a fixed control flow now has the like randomized control flow depending on the values of the X9 register. And also, we know since the Cascade fuzzer tries to create a program which is bound to terminate. So if we hit certain values, certain correct values, our program will terminate in the end. Next slide, please.
So the program execution is also a parallel task in Cascade. Each ultimate program is executed independently on a simulator designed under test. The output at this stage, which is given by E in the diagram, is a pair of values. The first value is a descriptor, which is a unique identifier for the executed program, allowing it to be regenerated. The second value is a success flag, which indicates whether the program terminated successfully, and optionally if the dumped register values match the expected result. Now moving on to automated program reduction. When a CPU fuzzer detects a bug, the initial test case that triggers it is often long and complex, containing hundreds or even thousands of instructions. These long programs make debugging difficult because they may include many irrelevant operations that do not directly contribute to the bug. And manually analyzing such large test cases is time consuming and inefficient. So, to solve this problem, Cascade comes up with the automated program reduction method. So, it starts by identifying the bug's tail, which is the last instruction of the bug. It does this by using a binary search mechanism to remove one basic block at a time. A basic block, as we know, is a piece of code without any branch or jump instructions. So it starts from the end and removes one basic block at a time, and till it removes the basic block, which causes the bug to disappear. So if by removing a basic block the bug disappears, we can conclude that that particular basic block had the tail of the bug. So now that we have isolated the tail of the bug, the next step is to isolate the head, which is more complicated than isolating the tail. This is because when you remove a basic block before a set of instructions, it can change the architectural state of the CPU, and so we may not be able to recreate the same bug. So to avoid this, Cascade makes use of a context setup block which preserves the architectural state of the CPU, which includes register values or privilege levels. So by using the context setup block, it preserves the architectural state, and again it eliminates one basic block at a time, this time from the beginning of the program to isolate the head. So by using this mechanism, Cascade is successfully able to isolate the bug, making debugging more efficient.
Okay, so now let's talk about the project evaluation metrics. So in this section, the authors talk about like three main things like coverage speed, bug detection, and program metrics. So coverage speed, like the authors compare their work Cascade with other works, which is like DFuzz RTL, RFuzz, and the HUZ. So all of these papers have their own different coverage metrics. So we have like control register coverage, which is basically like the coverage for measuring uh, all the register values which actually contribute which act as a control signal for a mux. We have multiplexer select coverage, which is like inputs are like which of the inputs are mapped to the output of a multiplexer. And we have commercial simulator coverage, which is like the coverage metrics defined by the simulator and it's used in the HUZ. We discovered like 37 new bugs in this paper across like five risk-free CPUs, and the program metrics which the author like talk about previously. So the since Cascade generates program which is bound to terminate, the completion rate of our programs in this paper is like 100%. Now prevalence, which is the percentage of randomized versus setup instruction, is high because like Cascade deliberately creates instructions which prioritizes having more randomized instructions compared to setup instructions. Also the paper tries to construct programs which are lengthy and randomized. So, and as previously mentioned, they have a higher instruction interdependencies compared to other fuzzers. Next slide, please. So here we have some like results mentioned in the paper. So the first graph is related to the control register coverage, where we have like time, the number of hours on the x-axis, and the number of coverage points on the y-axis. So Cascade with like both corpus is like using the previously generated test cases and live generation, which means like generating test cases on the go. In both the cases, it outperforms DFuzz RTL, which basically doesn't cross the gray line. Now we have simulator coverage, collected coverage, where we have number of instructions on the x-axis and simulator coverage is and how many of them are being covered. So uh, if you can see like the number of simulator coverage point, the Cascade fuzzer clearly outperforms like DFuzz RTL. And yeah, so next slide, please. Here we have multiplexer select coverage. As mentioned previously, we have data across like five different SoCs, which we have Pico, Kronos, Vex, Rocket, and Boom. And in all of those cases, Cascade clearly outperforms RFuzz. Next slide.
So to analyze the performance of Cascade, we have concluded that it performed well. It achieved 28 to 97% faster coverage than prior tools, namely the HUZ and DFuzz RTL, by generating 100% valid programs, which was less than 30% previously. It also discovered 37 new bugs, including 28 CVEs, which included privilege escalation flaws, and Zen bleed like hangs across five RISC-V CPUs. It also generated 10,000 instruction plus programs with 270 plus dependency chains. And by doing this, Cascade exposed deep vulnerabilities, proving that long and complex programs are essential for hardware security testing. Now, as you can see in this diagram, the average prevalence of fuzzing is around of Cascade is around 90.3%, which was significantly lesser before this. And the average dependency is around 9.5%, which was less than 4 previously. And the number of fuzzing instructions per program length is also significantly more in Cascade for all the 6 RISC-V CPUs that had been considered. Now, talking about the project evaluation for Cascade, whether they achieved their goals, we believe yes. They solved the low completion and high overhead problem. They surpassed state of the art fuzzers in terms of both coverage and bug detection, and they used automated reduction to simplify bug triage, which reduced the complex test cases from 10,000 instructions to just one instruction in some cases. Now, analyzing the strengths and weaknesses of Cascade, the main strengths of Cascade is that it is a novel approach to CPU fuzzing, and it employs a new method for debugging, which is the automated program reduction, which makes debugging significantly more efficient. It is also open source, which is another plus point. The main weaknesses of Cascade is that it is limited to RISC-V CPUs. Other architectures were not considered. There is also lack of discussion in the paper on how performance overhead in large-scale deployments would be affected. And there is also no hardware testing beyond simulation. So to conclude, I would just say that the main takeaway is that CPU fuzzers have inefficiencies, and Cascade solves this by cutting down on expensive bug detection overhead. It also uses automated reduction to make debugging easier, and it does all this while scaling up to handle longer and more complex programs. Thank you.